So, a couple of administrative notes first and foremost. Class is canceled on Thursday. This is because the Jewish holiday of Yom Kippur is on Thursday, right? I will send out an announcement as a reminder, but I will not be here on Thursday. I will post some videos to help. I'll post some videos, and if you could hit the lights on back there, that'd be great. Yeah, turn those lights on if you don't mind. Yeah. So I will post some videos to from previous semesters to help, I guess, tide you over. You know, don't want you to be missing me that much. So, but I will post videos for a video for, or a link to a video in the announcement for Thursday. But again, Thursday there will be no class, which means that if you have to make a commute, well, at least you get to make it later. That is basically the only time I should expect to cancel class for that. But also, you know, there would be a not insignificant minority of students who would not be here. So that's basically the administrative announcement. Second thing, okay, yeah, I need to publish these quizzes and adjust the due dates on them because they say September 9th because of the weird import thing I did. All right. No, don't publish the exam. Closed it. Oh, okay. So our solitaire encryption is due probably next week. I might change the due date depending on how people are doing that. So this is week 4, right? Yeah, this is week 4. So our exam, yeah, I'll change the due dates around a bit because exams will probably be around week. It will probably be, let's see. I'll say that our first exam will be in week 6, which is, so that means that basically it will be October 1st will be our first exam. Okay. That will cover all the way through linked lists and primarily focus on linked lists. Yes.
You said September 24th, so are you thinking about linked lists now?
Oh, hold on a second. Is this week 4?
Yes.
Then, I'm just worried with you. Yes.
Oh, no, I was just
Yeah, I'm just.
saying.
Yeah, no, I'm just. So I had previously said that it was the 24th. Does that match with people's recollection?
I think so. I think you said that like it might be the 24th, but I don't think it was a solid date.
Okay. Are there objections to?
First is also fine.
Okay.
Yeah, pick the first.
Okay. If there's no objections to it being on the 1st, then it will be on the 1st. If you cannot make it to the exam, please let me know that you cannot make it to the exam. If you wake up sick the day of the exam, please do not come in. Please let me know that you are sick. Basically, do not take the exam if you are sick. The exam will be on the computer. Now, in the labs that you're in, do you have access to computers or they remove the desktops? You have the computers in front of you if you need them? Okay. So, the exam will be electronic. It will be open note, open book, but I'll have some rules about like what kind of browsing on the internet you can do. But in general, if you can get to it from Canvas, it's good. Okay? If it's leaked on Canvas, that's fine. So that would include my YouTube. And that would include YouTube and the GitHub. Yes.
Would our notes count as, would our programs be very written for these assignments?
Yes. Yes. In fact, I highly recommend coming into the exam with an answer for one of the questions already written. Yes.
Can we use it on the laptop?
Yes. You can use it. You can use anything you would normally use for an assignment except for communicating with other people, essentially. Okay. Now, going back to that, how would you possibly know what one of the questions on the exam are? Well, I'll tell you what one of the questions on the exam are, because this is the exact same question that I give every single semester. And I will tell you it's important to figure out what the answer is. It's also a question on the practice exam, so I don't feel like it's so here's the question. I want you to be able to compare, or less of a question and more of a demand. Compare and contrast the performance of an array list versus linked lists within these three parameters. Memory usage, adding and removing from the array list and linked lists, and getting and setting operations. So memory usage, add, remove, and get set. Get and set and add, remove, they are paired because, of course, they're pretty much going to be the same thing for our usage. Yes, there's some subtleties for array lists and adding that you don't have to deal with removing, but those are, so now that you know that, and we will cover this in a bit more detail, you can come up right with an answer, with a good answer, and copy paste that into your exam, whatever your answer is. Right? Now, I would highly recommend using big O notation. Of course, I'll accept if you say linear time versus quadratic time versus constant time. But basically, you want to use the time complexity vocabulary in order to do that. Also, memory usage requires some more thinking because you haven't had to think about that yet. But you've got 2 weeks. And we will go over it when we go over the practice exam, which I will release soon. The practice exam will be much, much, much longer than the actual exam. Okay? Okay, now for the Module 4 assignment. You have 2 ones. You have 2 of them, and I said that the solitaire encryption, being harder, is worth 20 extra credit points. So if you successfully complete the Josephus problem, that will be 200 points out of 200. If you successfully complete the solitaire encryption, that will be 220 out of 200, which is not insignificant. This is because the solitaire encryption is a much more difficult one. However, should you find you need that the solitaire encryption, you decided to bite off a bit more than you chew, you don't have to start from scratch, because they're both going to use the same base file, which I'm going to talk about now, okay? So they both use the same base file, which is circularlinkedlist.java, okay? So I like this assignment because they both use the circular linked list. They both will use them in slightly different manners, and you'll want to focus on slightly different things. Can I not zoom in with control and, okay. Preferences, settings, font. '24. There we go. Can everybody see? No, let me go ahead and change the theme. Theme to default theme, light plus, because it's easier to see bright, I think. So can everybody see that, or do you need me to bump it up a bit more? Okay, great. So circular linked list, it's going to be, you're going to want to do this as a singly linked list most likely, meaning that all the pointers point in one direction rather than forward and backwards, because it's easier that way. You have less pointers to move around. The constructor, basically, you just have to set everything to null in that. In fact, you could possibly leave it blank, but it's good practice to set up your variables. You'll want to use getNode. That's going to pretty much be exactly the same as what I wrote in the videos, okay? In fact, there's no reason it shouldn't be exactly the same as what I wrote in the videos. Add, change this false to true for it to be correct over here for this add method. The main bulk of the work is in the add method over here and the remove method over here. You're also, if you're doing the solitaire encryption, will need to write a get and set method. Okay? If you're doing the solitaire encryption, you're going to need a get and set method. It's not necessary for the other method. And again, for get and set, because those are just get and set, you really don't have to make that any different than what you saw in the videos. So let's talk about the add and remove. Even though that this is a singly linked list, you're going to be using the same 5 cases you needed that I iterated over, that I specified in a doubly linked list. And this is because are going to be keeping track of the head and the tail of the list. Why? Because that's going to make it more, when you keep track of the tail, it makes it more runtime efficient. because you can just add to the end in constant time. So your 5 cases, the first one is you're just checking if it's out of bounds, just like I did in the videos. Making sure that you can, in other words, add to the proper index. Then these next 2 cases are very similar. Adding to an empty list and adding to the front of a list, right? Because when you add to the end of the list, you're technically adding it to the front of a list, right? As well as to the end, right? So these should be else if conditions over here, right? So when you add it to an empty list, there's nothing to attach it to, though. So you got to make it so you got to basically set it up to be both the head and the tail. When you're adding it to the front, right? Standard thing there, same with adding to the end. The difference here is that in all 3 of these cases, you got to make sure this linked list is circular. That means that you got to make sure that the last node in the list is going to be pointing to the head. So whenever you adjust the head or the tail of the list, just make sure to change everything so that, or change it and ensure that that last node and that the tail and the head are connected. Adding anywhere else, it's going to be exactly the same as anything else. Be sure to increment the size, by the way, to the list. And you'll want to increment the size after you attach everything. Otherwise, you could land yourself into a bit of trouble. Remove method is pretty much the same thing. Removing the only thing in the list means basically that you should set head and tail to null, so that's obviously a special case. Removing the first thing, right? You need to adjust the last thing to point to the beginning. That's one of the more common things here. Okay, removing the last thing and removing any other node. Now, over here I provided a toString method, so you can just simply print the list. It also has a tendency to crash if your list is not corrected, if your list is not correctly built. That is a feature, not a bug. It will crash if something is messed up in your list, so that you don't silently, so that you don't have these like silent errors that like things are disappearing. So what it will do is that it will keep going through your list and following the pointers until it gets back around to the head. Okay? Yes?
I have a question about the remove method after.
Okay.
So when I remove the first thing, that means the last thing just moves up. It doesn't move down like in an array list, like all the indexes.
So you don't need to shift anything when you when you remove the first thing in a linked list. Nothing needs to shift because you're just kind of chopping off the front, right? But what you do need to ensure is that the last thing is now going to point to the new head. Does that make sense? Or
So by the last thing, you mean the tail?
the tail always needs to point to the head, yes.
Okay, I see. Okay, yeah.
Mm-hmm.
Thank you.
Okay. Now also you may have noticed here that there's this public iterator E. By the way, I wrote this over here so that it has a circular linked list E. That means a circular linked list that takes in an E and an iterable. The iterable means that I can create an iterator from it. What the heck is an iterator? The iterator is the thing that objects have that allow you to use for each loops on this. I don't recommend using a for each loop on this guy because it'll go on forever. But the iterator itself is useful. And to get the iterator, you just simply call iterator, and it will return new list iterator, which is a private class in here. So now this is relevant for the people doing the Josephus problem, because it will make your job easier. Okay? What an iterator does is that it's got 3 methods. HasNext, which will always return true if there's something in the circular linked list, right? Because you can always go to the next thing because it's circular. A next, which will go to the next item, okay, in the list. So if the first time you call next, it will go to the first item in the list. Next will go to the second item. Index 0 and index 1, in other words. Okay? So you can just keep calling next and it will keep iterating over the items. But what's really cool is this over here, which is the remove. And this doesn't do your work for you. It literally, I feel very clever about this. It hooks into your remove method, which you are writing to remove an item. Okay? And what it will do, and so in other words, if you create an iterator after you add everything to the list, and then you call .next, and then .next, and then .remove, it will remove the item at index 1. And then when you call .next, it will continue on to the item that is now index 1, right? It will continue on to the next item. It automatically keeps track of everything for you. So you don't have to worry about that whole shifting thing that you did in the second assignment. As you can see over here, I already handled that kind of annoying math for you. This is useful again for the for anybody who's doing the Josephus problem. Okay. And there's your node class, singly linked list. Just simply takes in an item and sets it. Don't change it unless you want it to be more difficult, because if you add previous, it's going to be more difficult, because that means you've got basically twice as many pointers to adjust, which makes it messier. Okay. So for the Josephus problem, right? So let me just talk about a bit about the different problems if you haven't taken a look at them yet. The Josephus problem is based off of Flavius Josephus's a story from his life. Flavius Josephus is a historian who lived in Rome in basically the very first century, and his writings are basically they give a lot of historicity about how Judaism was practiced in that first century, as well as what I think is called Christian Judaism. Because if you remember, right, Christianity really hadn't codified itself yet until there were a lot of adherents of Christianity yet. So he basically was able to write basically about these Jews who were taking on new practices because who are all followers of Jesus. So he wrote about that, and it's basically we get some insights as a time period, which is interesting. So what's the Josephus problem? Has nothing to do with that, right? So just pointing out why Flavius Josephus is a historical figure. So he was a priest/war leader who rebelled against the Romans. In again that first century. This went poorly because all rebellions against Rome go very poorly. Rome was kind of the powerhouse of the day, and they basically made war of their business to be very good at. So anyway, his war band got barricaded into a cave, and they all decided rather than be taken as slaves, they would all draw lots to kill each other rather than be taken captive as slaves. Rather than, and not to commit suicide, they would kill each other. So they would draw lots, and then the last two people would kill each other. Anyway, so Flavius Josephus was left over and one other guy, and they kind of looked at each other, and I bet they went, well, this was a really terrible idea. And so then they surrendered and became slaves, and Josephus got his freedom 7 years later after somehow predicting that people who were good at generaling would win battles, so, but regardless. Again, I'm not a historian, but anyway, after that, he began writing a lot of stuff. So again, we know a lot about kind of religious histories of that time because of him, at least through his eyes. Because of course, I don't think he was trying to be an unbiased observer. Regardless, so the way that people think that, so with the Josephus problem, yes, that very grisly, the details there, horrifying in fact. But the way that was traditionally thought to happen is that basically people stood around in a ring, and then they would remove every other person from the ring until only one person remained. That was kind of the way that apocryphally, we don't really have any proof that this is the way they did it, but this is the way that the story has always told us how they did it. So the Josephus problem is, where do you want to be so that you're going to be the last person standing? Anyway, yeah, the problems you learn how to solve in computer science, right? Yeah, very relevant. Now, going on to solitaire encryption. Solitaire encryption is a real encryption algorithm developed for a fake person. in the book Cryptonomicon by Neil Stephenson. Neil Stephenson is a very prolific. He writes these door stoppers, books that can be better described as bludgeoning instruments. They are quite big. I'm partial to the book Anathem. Seven Eves was also a really good one. That one is about what if the moon suddenly exploded, and the ramifications of that, which is that we are not going to survive for very long if that happens because of the micrometeors. So, but he wrote a book about code breaking and code making in World War II, and in the 90s, which is when he was writing the book. And for that, he needed characters to be able to communicate securely without actually having any kind of encryption. So first off, when it comes to like code making and code breaking, there is only one possible completely impenetrable code that you can create, and that's called the one-time pad. That is where you create two identical pads of random numbers, hand them over to people, hand them over to hand one copy over to one person, hand one copy over to the other person. They're identical, and then basically for every letter, you take one of those random numbers and you modulate each number by that amount. So the first number is, if you want to write attack at dawn, if the first number is 3, then you would write D instead, and then you would send over the message, and then the person would see he got a D. The first number in my pad is 3, so I'm going to subtract 3, and I'm going to get A. This relies on doing modular arithmetic because you've got to be able to wrap around if you're at, but yeah, so that's the only way you can, and that way isn't, and that's the only way that's cryptographically mathematically secure, because that doesn't leak any information ever. The only way that can be broken is by applying a baseball bat to the kneecap. There is no completely secure algorithm because people are not secure. But it is basically as mathematically secure as you can get. Also, using encryption methods that basically rely on a secret method of encryption doesn't necessarily work, because eventually somebody's going to figure it out. And if the trick to encrypting is knowing the trick, then that's the issue. So there is something called the solitaire encryption, and that relies off a deck of cards to generate those numbers that you're going to modulate your message by. What you do is that you have a deck of cards, okay, and and what you do is that you, rather than creating one-time pad that are exactly identical, you and the person you're communicating with, you have 2 decks of cards that are arranged exactly in the same way that you hand off to each other, or that you memorize their starting configuration, such as we start with the ace of hearts and we go up by 3, right? You assign every card a numerical value, and then you basically say, okay, to generate numbers, I'm going to go through these 5 specific steps as to how I'm going to shuffle the deck of cards to generate a number. Okay, and then I just keep doing it to generate more and more numbers. I've got more videos that go into detail about this, but I don't want to necessarily eat up too much of the time. But I do have videos from previous semesters if you want to go perusing through it where I go into more detail. There's also a video linked. So the document goes into great detail about how it works, but also there is a video linked. Sorry, just so where's that? Yeah. Solitaire. Yep. Sorry. For some reason I wasn't reading it. Where I've got a video that's on YouTube of somebody performing it with a full deck of cards. For simplicity's sake, we're doing a half a deck of cards plus the 2 jokers. Why? There are 52 cards in a deck. There's 52 cards in a deck of cards. 52 divided by 2 is 26, which is a beautiful coincidence. Right? So we only really need half the deck of cards. She does it with the full deck of cards. And she does start with index 1 versus 0. But the point being is that she goes through the process and shows you how it works. So, which is the important bit about how she generates it. I also provide this file. Let's see what I provided in this file. Oh, great. And because you'll want to watch the video, I'll link to some of the previous videos about how I wrote these. But these are how you do, how you encrypt a letter in that way, where you modulate it by subtracting or adding a number. Where we take a key for that letter, that's what we call the number we modulate it by, and add it. So again, cryptography and cryptography, code making, and cryptanalysis, which is code breaking, have been always like intrinsically tied to warfare because you want to make sure that your orders can't be captured. And this started basically and one of the earliest kind of documents that we have of this is, again, the Romans. Not really a Rome buff, they just happen to show up a lot because they occupied a huge chunk of history. That's the Caesarian cipher, named after Julius Caesar, who basically said, okay, I'm going to encrypt all my things by giving every single letter the key of 3, which means that every single letter, when he wrote out his orders, he basically would write the letter 3 over. So again, attack at dawn, you'd move the A to D, and then T would be 3 letters down, and the next T would be 3 letters down. That's not too secure because once you figure out, because you only have to try 26 different combinations to figure that out. But like, when most people couldn't read, that was pretty good. And furthermore, when you were fighting barbarians, which were literally people who did not speak your language, that is like what barbarian meant to them, because all they sounded like were saying bar 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 bar. Although that's more from the Greek origins of the word, but regardless, it's a good story and a good way to remember where we got that. It's just people who speak differently from us, and we're going to make fun of them for that. Again, that was a pretty darn secure way of doing that, because even if you got somebody who spoke Latin and read Latin, they weren't necessarily able to do that. And the next way to do that was like to have a key word like snake, and you would modulate A by S's value and T by N's value, and then the A by A's value, and then the issue is, of course, repetition. Every there, and that could be cracked eventually. Doing some mathematical analysis. I'd be happy to talk about that in more detail at some other point. But the point being is that we eventually moved to the point where we needed machines to do this. So here, if you give it a letter and a key, it will encrypt it for you, and it makes use of the fact that notice this. This is the important bit. Letter minus A gives me an int. Remember, all your characters on your computers are just numbers. They're encoded into an ASCII value, so we just do a bit of math there. So what I do here is I subtract A out so that I can get them between 0 and 26, because A's value is like 71 or something. And then I get the value where it's between 0 and 25 inclusive. Then I add the key, mod by 26, so that it wraps over, and then I convert it back into a character by adding A. So basically I bring it down to 0 to 26, and then I move it back into the thing after I'm done encrypting. And then over here, because encryption doesn't play well with this, what I do is, rather than subtracting a key, I basically I add on to do a full rotation. So that basically if I was adding 3 to decrypt, I take what was encrypted, and to make the math easier for the computer, I add 23, because that would give me a full 26. So 3 plus the initial 3 plus the 23, which is like the reciprocal of 26, and I add that on. But these are the methods you'll want to use. I also split these up into step 1 and step 5. So for these steps, for what you're going to want to do for your 5 methods over here, okay? This is the important bit for these 5. For these methods, the easiest way to do it, believe it or not, is to create a temporary deck in each of these methods, and like add and remove the items until you get to the specific item you need. Rather than trying to remove the pointers, just like add and remove it. Like for step 3, where you have to take, where basically you take the top and the bottoms of the deck at certain points and switch them around, it's easier to just split that up into 3 temporary decks. A top, a middle, and a bottom. And then just simply re-add them back into the original deck. So using the add and removing method, try to basically limit yourself to adding and removing from the top or the bottom in these 5 methods. Yes.
Just a way to copy a linked list at once, or at least part of it.
I mean, the easiest way would be just simply to iterate through to the point that you want to
Okay.
copy it through and add those items too.
Okay.
Okay. All right. So that's what I've got for you. Any questions? Again, so I've got the outline for the code that you'll need for both of for the solitaire encryption. For Josephus, you don't really need that outline because you can do everything in main that you need. They're both challenging in their own way. Again, solitaire encryption involves more work. But if you decide that's too much work, it's not too much trouble to change over. Okay?